Hey there, welcome to this explainer. Look, if you're a college student currently staring down a completely massive pile of electrical engineering notes, I just want you to pause for a second and take a really deep breath. We are going to tackle this together, okay? Today, we're creating a calm, focused space to just study AC circuits. No high-pressure lectures, no rushing, just clear, visual understanding. Seriously, though, instead of looking at these circuits as stressful, abstract math problems, I want you to kind of shift your perspective. Try to visualize the electricity as a natural, breathing system, because it actually has a pulse, it adjusts to sudden changes, and eventually, well, it always finds its calm.
All right, let's dive right into section 1, the pulse of power, direct versus alternating current. So to really get how this system works, we kind of have to look at how electricity physically moves. On the left, we've got direct current, or DC. This is a constant, one-way flow. Think of it literally like water flowing steadily down a perfectly flat river. Now on the right, we have alternating current, or AC. This flow is totally cyclic. It's got a distinct rhythm, flowing back and forth, almost like the ocean tide breathing in and out. If you look at the classic graphs for this, you'll see exactly what I mean. At the top, there's that unwavering straight line of direct current. But right below it, we see the AC wave. Notice how it's a sinusoidal wave? That is literally the exact same shape as sound waves or ripples in a pond. It's a super common occurrence, not just in our circuits, but basically throughout all of nature. Moving right along to section 2, meet the circuit elements. Basically, our cast of characters. Before we get too deep into how the energy actually flows, let's ground ourselves with some real handwritten student notes. I absolutely love looking at these because it takes all these highly technical concepts and makes them, well, human and approachable. We're simply classifying network elements into two main buckets here, active elements and passive elements. Let's break that down nice and cleanly. Active elements, like your voltage and current sources, are basically the pushers. They're the ones supplying energy to the circuit, and theoretically, they have infinite energy handling capability. Passive elements, on the other hand, well, they're the terrain the current flows through. They either dissipate or store the energy, and their capacity to handle it is strictly limited. Let's look just a little closer at the unique personalities of these passive elements without, getting super bogged down in the formulas. Resistors dissipate energy. They're the friction, turning electrical energy into heat. Capacitors and inductors are more like storage tanks. They hold on to energy temporarily. And ideally, these elements are linear, bilateral, and time invariant. Honestly, that's really just a fancy way of saying they behave predictably. It doesn't matter which way the current flows, kind of like a two-way street, or exactly what time you measure them.
Okay, part 3, riding the AC wave. Let's make some sense of the math.
So, with our cast of characters introduced, the absolutely crucial thing to understand next is RMS, or root mean square. Since AC is constantly changing, it's peaking, it's dipping, it's reversing, how do we even measure its true impact? Well, RMS is simply our way of comparing apples to apples. It essentially finds the equivalent direct current value that would deliver the exact same average power to a resistance.
Now, I know looking at a dense page of integrals and equations can induce a bit of panic, but please, do not let it intimidate you. It is literally just mathematically proving the concept we just talked about. It's proving that an alternating current delivers the exact same power as a direct current equal to its RMS value. It's just a handy tool for translating a constantly breathing wave into a solid, usable number. And check this out. Right smack in the middle of all those complex equations, we get this single, incredibly simple number, 1.11. This is the form factor for sinusoidal waves. You get it by dividing the RMS value by the average value. I just want you to notice that, right in the heart of all that intimidating math, we arrive at this surprisingly clean, elegant number. It's a great reminder that there's a beautiful, simple order underlying all this stuff.
Which brings us to section 4, the temporary chaos. Let's talk about moments of adjustment.
Of course, circuits, much like your life in college, right, aren't always perfectly ordered. They face moments of sudden, abrupt change. When you flip a switch, the circuit doesn't just instantly know what to do. As these super helpful handwritten notes define it, a transient simply means temporary or short-lived. It's a voltage or current changing with time for a really short duration. Honestly, taking the anxiety away from the word transient is step 1. It's merely a fleeting stay of adjustment. Look at this wonderfully clear, hand-drawn graph. It shows that the total response of a circuit equals the transient response plus the steady-state response. That initial kind of chaotic curve on the left, that's the transient period. That's the moment of adjustment as the energy shifts around. But notice how, right after that, it eventually levels out into a calm, predictable flat line.
Sometimes, yes, the math describing this adjustment looks like this: literal pages of dense differential equations calculating natural responses and LC combinations. I'm showing you this briefly, definitely not to cause a panic, but to demystify it. These equations are just describing the decay of that temporary chaos we literally just looked at on the graph. Let's instantly give our brains a break from those dense equations. Seriously, whenever you see those scary formulas for transient analysis, just remind yourself of this one truth. It is just a mathematical way of watching a system settle down. The math simply describes the fading echo of a change.
And finally, Section 5, finding your steady state, the calm after the storm.
In the steady state, the circuit finally finds its absolute peace. The currents and voltages, they stop changing with time. This state always follows that temporary transient period. And what is so incredibly cool here is how beautifully simple things become. Under a DC steady state, an inductor stops fighting change and just acts like a short circuit, a completely clear, closed path. And a capacitor? It acts like an open circuit, completely breaking the path like a raised drawbridge. All those wildly complex elements just simplify right down into their most basic forms.
Remember, steady state always follows temporary chaos, every time. Just like a circuit settling down after a sudden switch is flipped, your mind also settles down after navigating a really complex, stressful semester. You go from the transient stress of learning a dense topic right into the comfortable, steady state of deep understanding.
So, as we wrap up our study time together today, I want to leave you with a thought about your own journey. What is your next steady state going to look like? Take a deep breath, trust the study process, and just know that the chaos is always temporary. Thank you guys so much for taking the time to study with me today. You've got this.